Hi guys, this is Jung Kyushin from Korea and I'm here to present our latest work, Task Planning for Long Horizon Cooking, task based on large language models. Our research focuses on long horizon task planning using a deep learning framework to automatically generate task plans based on a user-defined target. While this work targets complex multi-step decision making for real-world tasks such as cooking. Each step requires an object-oriented descriptions specifying actions, object, and related states for robots to execute. Task planning is challenging due to the complexity of these long sequences. So robots need to understand how each step affects the next. Like for instance, if making a carrot salad, the carrot must be cut before boiling, like otherwise it's too large to process. Our main goal is to train a framework that enables a robot to understand both the semantic features of an environment and the sequential relationship between actions. Previous works employ a deep learning network and train it with the annotated object-oriented datasets. These works understand the environment on two approaches, symbolic representation or image-based representation. Symbolic representation is a method that understands the environment by predefined labels for each object, where image-based methods directly understands environment via image feature itself. Recent works for task planning adopted large language models. They form the task planning process as a prompt engineering using in-context prompts to specify an environment, and by specifying certain need as a sentence, these works expect the LLM to generate a task plan as it generates the sentence. However, these approaches also have several limitations. First, for symbolic representation methods, they struggle with real-world objects that lack predefined labels. Like for example, while symbolic methods can manage labeled objects like bacon or butter, they fail when encountered with unlabeled items, such as ham or red onion. This limitation possesses a significant challenge as the real world contains countless objects that may not have predefined labels. And for image-based methods, on the other hand, they face a non-deterministic challenges. Robots using an image-based methods often struggle to identify objects within an image, leading to an issue of partial observability and inconsistent performance. LLM-based methods also have their drawbacks as well. First, they are computationally intensive, which creates high overhead. As many of you know from using the models like GPT, the processing time can be somewhat substantial. And second, the autoregressive generation of LLM is unconstrained, which means that they can produce outputs that don't align with the real-world constraints, like such as suggesting ingredients that are not unavailable. Well, this phenomenon, often referred as an hallucination problem, occurs sometimes. And lastly, training dataset presents another challenge. Object-oriented structures require highly detailed labels of each action in its smallest units, which demands an extensive human effort. This limits the amount of available training data, reducing the framework's ability to fully understand the complex semantic context and hindering its overall performance. To address this limitation, we propose two frameworks. First, a software generation framework that generates tasks based on a linguistic feature. We use a language model to only extract the linguistic features of a given environment, and based on the feature, add a lightweight neural network to generate sequence of actions. And second, we also propose a LLM-driven pseudo-dataset generation framework to crawl dataset from the internet, complementing training dataset, thus enhancing the model's knowledge and adaptability without any human supervision. This is the graphic visualization of our deep learning framework for our software generation. For our input, we give an environmental information such as food ingredients for cooking and cooking tools. And also, we give a target recipe in a natural language format, so our goal is to generate a long sequence of task plans for the given target. We compose our framework in three steps. First, with a given environment, we assume the success of a off-the-shelf object detection and transform the given ingredients into words. Then, we employ a pre-trained language model to extract the linguistic features of an environment in the target. We denote that the language model is frozen, meaning that it does not update the training. We assume that the language model inherits sufficient semantic knowledge for the task and aim to directly employ its knowledge. each object and the target is transformed into a token feature, which inherits the linguistic representation features. Next, based on the extracted token feature, we employ an object encoder. This encoder is a type of a transformer layer which understands the set of ingredients. The role of each ingredient may vary depending on the set of the combination, and the object encoder interacts each token feature and understands the local global features of an environment. Then, we employ the outputs of the object encoder as an environmental representation feature. And finally, we employ our novel memory augmented decoder. This takes the environmental token for the present time step and the external memory feature from the previous time step, and the output of the decoder is passed onto a recurrent layer, GRU, and with the output we feed it to a simple multi-layer perceptron to predict the action, object, and the states optimal for each step. The output of GRU is saved in an external memory to represent the features of a current step to be used for the next step, and this way we enable the model to learn the sequential information between steps. Furthermore, we propose a framework to complement additional data for training without human supervision. Object-oriented structured dataset for a robot due to its explicit nature requires a massive human labor. And as mentioned earlier, this limits the size of a training dataset. However, the knowledge that is required for a robot is abundant on the internet in a natural language format. So, our intuition is that training the robot framework with this knowledge in a linguistic format would enhance the task planning to adapt to unknown knowledge. And so, we create a framework that crawls the information from the internet and transform it into an object-oriented structure using LLMs, and retrain the robot with this data for knowledge enhancement. To start with a given target recipe from a user, the robot calculates the uncertainty of a given target based on the cosine feature distance by comparing the linguistic feature with the previously trained target recipes. So if the distance is over a certain threshold, we assume the target is unknown. Then, for our unknown recipe, we crawl the recipes from online based on the target recipe keyword and gather a set of linguistic description. Then, with the crawl description, we employ an LLM to transform it into an object-oriented structure for our robot to understand. We use the in-context learning strategy, which we provide the rules of the object-oriented structure and the following example as an in-context prompts, and then you give the natural language description to transform. As a crawled language description may not contain the information it needs, we apply a rule-based filtering to exclude unfit descriptions. And for this, we will explain how we filtered out inappropriate descriptions in the following section. And lastly, we train the task planner based on the generated pseudo-object-oriented dataset. The task planner now possesses a knowledge for a given target recipe, and this enables the task planners to understand and process the human need even if it is never trained. This is a process of filtering natural language. The upper text are the appropriate cases about a recipe, however, the text below is a case of a wrongly crawled text. To filter out unsuitable cases, we first feed all the text into a large language model. So in this step, we explicitly aim to extract the action, object, and the state information from each sentence, maintaining its precise wording. Regardless of the appropriateness of the input text, all descriptions are converted into an object-oriented structure. So we then apply the rule-based filtering to sort out these structured results. Our rules are based on the principles of the object-oriented format. So if the output generates an incorrect number of keywords like for 3 or 2 or 4 for the object-oriented structure, the entire recipe is discarded. We thus tag each selected keyword by its part of speech. And if the word does not fit in its assigned section, like for example, if only a noun appears in the action part, we also exclude it as well. And finally, if the collected keyword does not match the exact format within a sentence, we assume the hallucination occurred and exclude it as well. With the filtered sample, we propose the LLM again to refine the words within an object-oriented structure to satisfy the robot capability. We change it to fit the predefined action capable for robots. So in this case, We filter out once more to exclude the recipes that robots cannot perform. This is the training dataset for our task planning framework. To initially train our task planning framework, we employed the existing public dataset, FUNETs, with 20 food recipe, each augmented through changing order or object replacement. The augmentation was strictly supervised by humans, and for the unknown recipe, we randomly added 50 unknown food recipes that is classified as uncertain and generated 1,708 object-oriented structure using GPT-3. We attempted to crawl for the description for each recipe and filtered out about 60% of the descriptions. Each evaluation set contains at least one or more unseen objects from the training dataset, and for each target, 21 tasks that are required in the average. And this is the quantitative results. We evaluate the planning based on the success rate. Compared to the existing recurrent methods that use all-RN transformer and memory-augmented transformers, our work showed the best performance. As for the trained recipe data, ours showed 95 success rate, and with the unseen recipe, the success rate dropped to 35%. However, with retraining the model with LLM-generated pseudo dataset, we improved the success rate to 62% without any human supervision. We also performed real-world experiments with the robot arm. This is a video case of a brownie as a target, and we give 9 ingredients in total. Lemon was not given during the training process, meaning that in the training process with 20 recipes, the model have never saw a lemon. However, it understands the semantic feature of a target recipe and ingredients, and thus created a own process to use these ingredients. This shows that employing a linguistic feature for a robot task planner could enable a process of unseen objects or unknown environments. Thus, LLM could enable a continuous training for robots to adaptively learn knowledge to complement the uncertainty. Thank you for this listening, and this is all.